Hello everybody and welcome to example 1. We are looking at page 33 in the workbook here. And this is going to be our first example of finding the volume of what's known as a surface of a solid of revolution. Okay, so let's read this problem together. So they'd like us to find the volume of the solid region generated by rotating the curve y equals sine of x about the x-axis on the interval between 0 and 2 pi. Okay, now the first time that you see a problem like this, it takes a couple of minutes maybe to wrap your head around it and really see what this is asking. Okay, so let's draw a picture together here. Okay, sine of x between 0 and pi, that's like half of a period of the sine function. So it kind of goes up and comes back down over at pi here. All right, and they're asking us to rotate that curve about the x-axis, okay? So here's how I want you to picture this. Imagine that the sine curve that we just drew is a wire, and we're going to take that wire and we're going to fasten it to the x-axis at those 2 points. So it's fixed there, can't move. And I want you to think of taking that wire and giving it a push into the paper here, and imagining that that curve can rotate around the x-axis. Okay, so again, it's fixed at these points, but the curve itself can rotate. It's going to go back into the paper, and it's going to come out down below, and you're going to see a mirror image of that curve that looks like this. And can you imagine the three-dimensional solid shape that's being traced out by this curve as it moves into the paper, comes out down below, and just keeps going around the x-axis? Okay, I'm kind of seeing maybe a shape that looks like a lemon, maybe a football or something like that. That's sort of what we're looking at head on here. That's what we're trying to find the volume of. Okay, and the approach for finding the volume is going to be similar to the approach that we used in the redwood tree example above. We're going to do a slicing approach. Try to find the volume of this slice by slice. Okay, so now I want you to imagine taking out a machete, big machete, and slicing this thing kind of perpendicular to the axis of rotation here. All right, so I want to write something for you here. So imagine taking a slice. We're going to take this machete and just slice straight through this. My question to you is, if you were to take a football like the shape that we are and just kind of slice it down the middle and turn it towards you so that you could see that slice that you cut out, what's the shape of the slice going to be when you look at it from the front? If you think about it, what you're going to see is kind of a circular slice. Okay, something like that maybe. Okay, and our approach then to finding the volume of this whole football is to first think about what would the volume of that little slice be, that circular slice that we just chopped out. Okay, so down below, I'd like to draw a front view of the slice. Okay, so imagine taking that circular slice and just turning it towards you so that you're looking at it from the front. And first step to finding the volume of that slice is thinking about what is the cross-sectional area of that slice. Okay, so how do you find the area of a circle? Okay, you might remember that the formula for the area of a circle is pi times the radius squared. Okay, so we're interested in the radius of that slice. Okay, but what is the radius of that slice that we cut out? Okay, well, it kind of depends on where we did the slicing, doesn't it? Okay, so the radius is going to change depending on where we took the slice, and in general, what measures the radius is the distance from the x-axis up to the curve, whose equation just happens to be y equals sine of x. Okay, so in a nutshell, this radius is going to be given by the function itself. It's going to be sine of x because that's the y value. That measures the vertical distance from the x-axis up to the curve. All right, so with that then, we'll use the formula that we just mentioned for the area of the slice. We're going to get pi times sine of x. Okay, let me write this a little bit more neatly here. pi times sine of x squared. Okay, and to find the volume, we're going to take that cross-sectional area, pi times sine of x squared, and we're going to multiply it by its thickness. Okay, think of the thickness on our picture as just being this little distance in the x direction. We're going to call that dx, just to emphasize the fact that that's a very small horizontal distance. Okay, so pi sine of x squared dx, it's like the volume of a very thin cylinder on its side. Okay, but so far, we've just got the volume of this one slice. We would like to get the volume of the entire football-shaped solid that we have here, and so we're going to do that by adding up the volume of these slices, and that means integrating from the left-hand side to the right-hand side here. Okay, and you can see from the picture what the limits of integration are. We're going to start at x equals 0 and end at x equals pi. Okay, so we're integrating from 0 to pi. Okay, if we can do that integral, we have found the volume of this solid of revolution. Okay, first thing you might notice is that this pi is a constant, so we can pull that out. And then what we have to integrate is the function sine squared of x. That's not a particularly pleasant function to integrate. And so here I'm going to recommend going to the integral tables. Okay, you'll find a formula that matches this very nicely. Okay, in fact, formula number 63 works nicely here. So formula 63 tells us that an antiderivative for sine squared of x looks like 1/2 x minus 1/4 sine of 2x. We're going to evaluate that between pi and 0. Okay, and the rest is just kind of substituting in limits and seeing what we get here. So if we plug in pi for the upper limit, okay, we're going to get 1/2 pi minus 1/4 sine of 2 pi, minus the lower limit, 1/2 of 0 is 0, minus 1/4 sine of 2 times 0 is 0. Okay, and the nice thing about this is that there are a lot of zeros in this problem. Okay, so sine of 0 is 0, and sine of 2 pi and 0 are actually the same angle, so we're going to get 0 there. So really everything goes away except for that 1/2 pi. Okay, and that's being multiplied by pi. So our answer is just going to wind up being 1/2 pi squared. Okay, there is the volume of this solid.